Let's see an example. So we're considering the Daniel cell, the one that we've already seen in topic 9.1. So in the Daniel cell, you have zinc in a solution of Zn2 plus, copper in a solution of Cu2 plus. And from the data booklet, you can find the standard electrode potential of these two half cells, and by default they are as reduction processes. So first we need to find which one is going to be the cathode and which one is going to be the anode. So based on the values, the more positive value is going to be the cathode. So this is the more positive value, therefore this is going to be the cathode. Therefore, the zinc is going to be the anode. Here. So we've noted down the two standard electrode potential values. Now we're going to write the equation placing the cathode and the anode to determine the overall equation. So the reduction reaction is going to stay the same. So at the cathode, the equation is going to be the same as it is in the data booklet. So I'm going to look at the value at the equations. So I have a solution of Cu2 plus in contact with copper. So Cu2 plus in contact with copper. So this is the half equation in question. So this is reduction, so it's going to stay as it is. The next reaction is zinc solid in contact with Zn2 plus. So zinc solid in contact with Zn2 plus. And this is the equation. Now, because this one is the anode equation, so at the anode you're going to have oxidation. The equation given in the data booklet, this is a reduction equation. Right? So we have to flip this over. So we're going to flip the equation at the anode where you have oxidation, cathode will have reduction as such. Now when you're writing the equations, do not include any reversible arrows, because we have already decided now which direction the reaction is proceeding. So we know which one is oxidation, we know which one is reduction, so it's not reversible anymore. Also, do not reverse any sign. So see, even if I have flipped the equation, I haven't flipped the sign, so the sign stays the same. I'm not changing the sign. So overall equation, I'm just going to add these two. The electrons will cancel out. They should cancel out. So I end up with the overall equation like this. Here. Now let's find the overall standard cell potential. So the overall standard cell potential is going to be the standard electrode potential of reduction minus standard electrode potential for oxidation. So reduction is here, so plus 0.34, which is the more positive, minus the more negative value for oxidation, so minus 0.76. So when you compute this, you get 1.10 volt. Make sure that you include brackets so that you can flip the sign as required. Do not try to flip any sign before him. You might get confused when to flip and when not to flip. So it's better that you don't flip any sign and that you compute it using the equation reduction minus oxidation. You're always going to get it right. So for the cell diagram, we'll start with the salt bridge. Oxidation on the left hand side, reduction on the right hand side. So oxidation, you have Zn solid in contact with Zn2 plus, and reduction you have Cu2 plus in contact with Cu solid. I'm also going to include the standard electrode potentials of each. This formula also applies. The overall standard cell potential is the electrode potential on the right hand side so this one, minus the electrode potential on the left hand side, which is this one. So you still get the same value. So let's see the example. Another example. So find the overall standard potential of the cell shown below. So the cell diagram is already given to you. So you know that this is oxidation side and this is reduction side. So you know that the overall standard cell potential is going to be standard cell potential of reduction. So minus standard cell potential for oxidation, so that you get this value. Now this confirms the idea that the further apart the two metals are in the reactivity series, the higher the voltage that we're going to get. Let's try the equations now to find the overall equation. We'll start with the reduction reaction, which is going to be the same as from the data booklet. So we have Ag plus and Ag solid. So Ag plus and Ag solid. So this is the equation in question. And for oxidation, you have aluminium forming Al3 plus and free electrons. So you have loss of electrons. Overall equation, the electrons should cancel out. So I need to multiply the equation of silver by 3. So I'll multiply this by 3 so that the free electrons cancel out. So I end up with the overall equation 3 Ag plus plus aluminium. So I include the state symbols, giving 3 Ag solid here. So this is the overall equation with the overall cell potential of here. Let's try example 3. So we have Mg2 plus and Mg and nickel 2 plus half cells. So first we're going to look at the data booklet, and we're going to find the standard electrode potential of both of these. So this is what I got from the data booklet. Now let's see which one is going to be the cathode and which one is going to be the anode. So the more negative one is going to be the anode, and the more positive one is going to be the cathode. So if I look at these two, this one is the more positive one, closest to 0. So this is going to be the cathode, and this one is going to be the anode. So at the cathode, I'm going to have a reduction reaction. So it's going to be the same. At the anode, I'm going to have an oxidation reaction, which is going to be the reverse of this. So I've not used any reversible arrow when deducing the half equations. State the equation for the overall redox reaction. So I'm just going to add these two. Then deduce the EMF of the cell. EMF is the overall standard electrode potential. So it's standard electrode potential of reduction minus oxidation. So reduction is here. Oxidation at anode is here. So this gives me, so this is the EMF value. Draw a simplified cell diagram using correct convention. So I'm going to have the salt bridge. On the left hand side, I'm going to have the anode, and on the right hand side, I'll have the cathode. So the anode has Mg solid in contact with Mg2 plus aqueous, and the cathode has nickel 2 plus aqueous in contact with nickel solid. Now explain why a half cell consisting of inert platinum electrode in 1 mole per dm cube of aqueous solution of sulfuric acid in contact with hydrogen gas at 100 kilopascal at 298 Kelvin cannot be considered as standard hydrogen electrode. If you still remember standard hydrogen electrode, you need hydrogen gas in equilibrium with H plus, and H plus should be 1 mole per dm cube, and this should be at 100 kilopascal, and this should be at 298 Kelvin. this is satisfied, this is satisfied, and this is satisfied. But this one, if you look at sulfuric acid is a dibasic acid. So when it dissociates, 1 mole of sulfuric acid gives you 2 moles of H+, which means that 1 mole per dm cube here produces 2 mole per dm cube of H+. So you don't have 1 mole per dm cube of H+, therefore this is not a standard hydrogen electrode. So this is the answer. The fourth example, determine the overall cell potential for the Vertex cell given below. So overall electrode potential is going to be electrode potential of reduction minus electrode potential of oxidation. The reduction one is the one which is more positive, so the one which is more positive is this one, therefore this is going to be reduction, and here you're going to have oxidation, so it's plus 1.6 volts minus 1.51 volts. You're not going to flip any sign, you keep it as it is. So you have 0.09 volt overall. Write the equation for the overall reaction. So overall reaction, this stays the same because this is for reduction, but this one is going to flip because this is for oxidation. Now you're going to adjust the number of electrons. So 5 and 2, this is going to multiply by 2, this is going to multiply by 5. The number of electrons cancel out, so you end up with this overall equation. Note that the H2O and the H+ will also adjust themselves. So 10 and 6, so it adjusts. So you have 6 H+ on this side. Here you have 8 and 5, so 8 minus 5, so 3, because you have more on this side, so 3 H2O here. For this question, it's asking you to draw the cell diagram. Actually, because you have aqueous and liquid over here, you're not going to be asked to draw such a cell diagram, so you can just ignore this question here.